Hey, good afternoon, everyone. Thank you all for joining us today in our weekly webinar series. Today our featured topic is PON and FTTH. My name is Jessica Petrohoy, and I'm the Marketing Coordinator at FiberOptic.com. FiberOptic.com is a leading provider of fiber optic products, training, and rental equipment. We're pleased to present this topic to you today. So with us today to talk about PON and FTTH is Jack Ioneer. Jack is one of our senior instructors and a field technician with over 25 years in managing and testing networks. And Jack will be discussing active and PON design, installation practices, and maintenance and troubleshooting. Remember that our webinar series are available to you online at fiberoptic.com/webinar. And when Jack is finished, we'll take questions from the GoToWebinar question box at the bottom of the screen for a question and answer session. So thank you again for joining us today, and at this time I turn the presentation over to Jack.
Well, good afternoon, everyone. My name's Jack Ioneer. Just a little bit about my experience or credentials. I am a former BICSI certified instructor, and I am currently a BICSI RCDD for design and, of course, a BICSI technician. I'm also ETA certified to proctor their exams, and along with the TFS certifications that you might expect me to have with this current company. Today's topic is about passive optical networks, or basically fiber to the X as you see up there in front of you. And it's a quick overview. Most of this comes out of our Certified Fiber Optic Installer program with the specialty of fiber to the home. So it's got quite a bit of content in it on our online training. And I'll explain that a little bit as we go. So you're going to get a little bit of what's on the okay, click there. There it goes. Well, as I said, these slides are really components of our online specialty training module, FTTX. And if you're taking this online, in addition to the first two modules, which are basic fiber optic theory and basic installation for our certified fiber optic installer, the additional module here is specifically for the specialty fiber to the X. Now, as you can see down here, the whole thing would cover active and passive design, basic installation practices, splicing considerations, connectors and enclosures and panels and such. In the class, to actually get a certification, you can see here a little bit of what we would do with the hands-on exercises should you elect to take that certification. But it's basically we prep a small closure, do some pigtail splicing and fusion splicing, and then we basically test a PON circuit, basically from the house to the curb, from the curb to the FTTH, maybe at the top of the street. And we do topics like that. We have a test mock-up. So I guess we start with a question of why fiber to the X or to the home. And you see up there, so some of this is a little bit old, but you know, it's all about speed, isn't it? You can sit and watch your television and watch the Comcast and Time Warner and everybody fight over how fast they are. But when you get, it is about higher bandwidth and higher speeds. And if you think back to the dial-up modems, which, you know, there are still areas of the country that may be using that normally 56K just isn't good anymore. But today's acceptability goes anywhere from 1 to 3 megabits, and if you want usually some little extra money, you can get between 35 and 70 megabits per second to your home or more. As I said, it may cost you a little bit. So in this, we talk about options for delivering the bandwidth and what the providers are dealing with where we have mixed network architectures. So often we don't just scrap the old for the new. You know, infrastructure is quite expensive to build. So often what you see here is we'll have ways to deliver passive optical networks or higher bandwidth fiber over, and the first bullet you see there is legacy, which is the old ADSLs or VDSLs. And then we have FTTN fiber to the node, which brings fiber to about 3,000 feet, say, of your home. And FTTP, is typical fiber to the premise itself. And you see on the drawings various areas where we go fiber and convert. So there is ways to use existing infrastructure and even copper infrastructure. The other thing we discuss, or if you're doing layout or design of anything, is that the impact on the environmental. And by this, I'm pretty much talking about the environmental of our operating network. So temperature, particularly cold temperatures, can cause a wide variation. And it's all related to losses and failures due to cable and cold temperatures. And cable assembly shrinkage. And since most of a fiber cable is probably 90+% plastic, it does have an impact in extremely cold temperatures. And of course, Mother Nature and planning for the worst case. Now here's back to that first slide where we put some terms to it, our first term. So you often hear fiber to the premises, and you'll see that depicted on FTTP. And so the little X is just a placeholder. And then we have fiber to the actual home, H. Fiber to the business, you'll see referred to as B. Fiber to the curb, if they're just doing my neighborhood and putting a vault at the end of my driveway, but I haven't signed up, it's basically to the curb. And then fiber to the node, it's kind of reverse order what that original drawing was. It shows that we run to a mode to a certain point in the neighborhood and then utilize existing metallic cables. And that's what they mean by FTTN, or fiber to the node. If you do have questions, I'll try to answer them. You don't have to wait to the end. If they're pertinent to what they do, I can probably answer them on the way in. So I'm going to leave that screen. Feel free to go ahead and do that. Well, back here. So what does that mean? It basically means from the central office to your premises that we have no active devices. And that's what we're going to start with, a few basic powered components. One is referred to simply the OLT, or optical line terminal, and that's at the central office. Could be at a hub, but that's at the central office. The second power device is the actual device that's mounted on your home. The old copper guys, it's a NID, some sort of network interface device. It's an ONT, and that's located at the home or the business. That's the second power device. So as the term indicates, that it's a passive optical network, that there's no active components until it leaves the central office until it gets to your home in this case. Now notice that the basic scheme can go passive for up to 20,000 meters from the office or the central office. So that puts a couple basic components into line. The other terminology you hear all the time, and it impacts on how a provider might deploy these new networks. And the first term you commonly heard are greenfields. Well, they're newly built areas, so there's no existing anything. So there's actually no constrictions. They could be new neighborhoods or planned communities. And there are some pluses that the provider can get when everything's new, and cost of installation, shall we say, or investment, that would greatly reduce that. So green fields typically can be a single family home in a development, but they can be multi-dwelling units such as apartment complexes or small business parks. The other they often referred to as brownfields or overbuild. The overbuild simply means that it's existing, and if it's a new deployment for a company to provide service, often there's already cable TV coax by the cable TV provider already in the neighborhood. So if you're the likes of, say, a Verizon with Fios, you must install, or you would install, fiber directly to everybody's house in order to compete in the voice data / video arena, or the triple play that you hear so much about. That offers some problems to a new provider of services in that he doesn't have an in-ground infrastructure where the cable TV provider would have usually an in-ground. And that's what we mean by overbuild, or sometimes you'll hear them referred to as brown fields. Now, the passive optical networks use a combination of splitters. And that basically says that a single fiber optic cable coming out of the central office can feed up to at least 32 individual homes by way of a passive optical splitter. Now, where these splitters are placed in the physical infrastructure would depend. And there are two basically classifications. I can do what they call a centralized approach. Now, as you see on the bullets, it's a lot to read, but it really, the optical line terminal cards have much efficiency because each fiber, say 32, they're split at the central office and each home has their own fiber back to the central hub. So the efficiency of the electronics back at the central office is much improved, or very efficient. All of them are used properly. Now that could be extremely important when you see on their initial takes. Well, that just refers to the fact, and again, Fios and Verizon, but any company installing fiber to the home that doesn't have existing high bandwidth cable solutions would be faced with the same thing. And it simply means if you have a neighborhood of 100 homes, for example, and 90 of them have Comcast, and I'll just pick on Comcast, and 10 of them have the dish, well, you have to build out the whole neighborhood, but your take rate may be very low, meaning you've got to win the business over. You have to build for all of them, but maybe you're going to get clients in dribs and drabs, 1 and 2 at a time. So that's what we mean by take rates, and that might determine how you structure your physical structure. The other one is cascaded splitters, where we can dedicate 32 fibers, go to a single 1x4 or 1x8 back to the central office. This would be at, say, the FTTH at the, say, top of the neighborhoods. It would require homes to be in a basic same vicinity, and the access terminals would have to be top. Now that's all we meant by that, if you can picture the physical structures. Now, there are PON standards, so who writes the rules? Well, standards committee. And you're going to hear this technology or this terminology thrown around. So if you want to think of APON, which is a asynchronous transfer mode PONs, use the old ATM networking for transported data. And it was followed by BPONs, or broadband PONs. So you see a typical drawing here of internet services routing through a router into some sort of network equipment. And it would include wave division multiplexing, video overlay, higher upstream bandwidths, and upstream allocation of bandwidths. So let's just call that at least the second generation of networking, maybe still implied today. Now, if you look at what I call here the various flavors of PON, and this depends since about 2084, what do we do? Active Ethernet platforms can carry the data signals, and of course the voice today, can be located up to 120 kilometers, not 20, without geographic restriction. Now, what am I talking about here? Traditionally today, the triple play is loaded onto the network almost as if they were separate systems. And you'll see another drawing that kind of depicts that a little bit better. But there's no reason the Ethernet protocols or network could carry all video, voice, and data and actually gain some efficiency on it. There are some cases where municipalities, towns may buy all the triple play, let's say from a Comcast or a Verizon, but then go around their community or municipality delivering all Ethernet as their fiber to the home solution to the locale. But that's EPON, or Ethernet PON. If we continue, then the next generation up is a GPON for gigabit. And that's totally IP-based protocols. And you can see here on the little diagram where the internet, including your different switches, are layered into multi-gigabit accesses. For this today, all we really need is a GPON. That's a typical diagram of what you would call today the triple play. Now, here's a pretty good layout. So APON was the first, and there are ITU standards that you often hear their bases. So it was a G9.983 was APON, 984 was BPON. So this is strictly an evolution. Then GPON was an evolution of 984, which supported higher rates and enhanced security than did the original 984 standard. And then here we say an active Ethernet platform can be up to about 120 kilometers. But you see a very simple, say to 20,000 typical length, where we have a 10G GPON OLT, and on a certain wavelength we inject the RF video equipment. So you now have the signals flowing upstream and downstream, as you see, through a series of splitters. And we'll talk about what wavelengths do what. But that's the basic. Now, we started out just a few minutes ago with the advantages of centralized splitters. And there are two common configurations, as we said. Central, everything's back at the office, and cascaded, in which they're brought out to the field and split at various convenient points. But eventually, 32 homes can be fed from one single mode fiber. Now, I'm not going to spend, I got a lot of slides for the time slot, so I'm going to try not to repeat myself. If you need any clarifications, this is just a diagram where one fiber is split 32 times at the central office, and of course each fiber is bound for your home, as you see there in a simple drawing. Cascaded, a fiber is split at an outside plant enclosure and then split to the various homes. So you move the splitters out to the field a little bit closer. Hence the term cascaded. Now, we already kind of mentioned why the centralized approach. If everything's back at the central office, then you have an efficiency of populating these OLT cards, and you get a much greater efficiency from that port. Well, part of it is the ability to test the networks. And it's also nearly impossible. We're not going to get to the testing phase on this, but in the course we do deal with it. But the ability to easily test and troubleshoot, because it's almost impossible to see down individual fiber lengths through a series of splitters. We can see, but almost impossible to see. So one centralized hub for troubleshooting ends up instead of two or more. That again goes back to the central, that I can shoot out to where the splitters are from the central office and then go to the other side of the splitters and split to your homes. So anyway, all the splitters in one location make it pretty easy to break down the circuit for ease of testing and troubleshooting. Now, there are three basic tests that we do: end-to-end link or assertion, optical return loss, and mapping or characterizing by way of an OTDR trace. Now, the 1x32 splitters allow the OTDR to trace upstream to the central office and then downstream, as I said, to the access terminals. Connector ports are available in the hub and enables testing. So we can do that as we turn up each individual customer signing up for service. Now, when you calculate budget losses, or if you look at the budget losses through a splitter, it's some pretty basic stuff. You may have had some of this at basic electronics, but we're going to have a pretty high losses in this physical plant. Unlike what we normally think of on a pole for normal telephony, our losses are going to be pretty substantial. And it comes from the fact that the splitters are passive and they split the signal. This is not unlike a typical cable TV coaxial or RF splitter. In fact, all of the light still goes around the 3 dB rule of power, which means every change of 3 dB you double or half. So what we want to take a look at is, well, what are the losses through these splitters? You heard me say substantial. And this is pretty much a little chart that calculates it so you don't have to do the math, so to speak. So 1:2 splitter, which is a 50% split of the power, or the light signal ratio, gives you 3 dB loss. There's your 3 dB rule of power. A 1:4 would be 25%. A 1:8 splitter would be 12, roughly 9 dB loss through the splitter, and a 1:32 would be 3.1%, or about 15 dB loss through the splitter. So you can see splitting does take a considerable amount of loss. And that has to be added into the calculation of budget losses and power consumption. Which means you have to add, there's a thing called uniformity, and basically that is added to your loss budget. And there are some tolerance stack-up issues we don't need to address at this time. In a centralized approach, everything's back at the central office, so that's a little easier to control than when the splitters are placed further out in the field. So there's a couple architectural decisions that you must look at when you consider, well, where am I going to position this? Well, this isn't a full design class, so we just give you an idea of some of the things that we have to do. For instance, basic function in the central office is to connect OLT to the outside plant fibers at the office. They'll often deploy wave division multiplexing to enable voice and data to be combined with the video signals, and then the proper placement of connector interfaces. And as you say, how do you turn up service? So there's a couple of options, and you may see depending on what plant you're doing. So the business customer might order an OC3 line, optical carrier 3. How do you maintain flexible access both to commercial and the traditional, quote, cross-connect? In the CO, it's a well-established strategy for routing and cross-connecting your cables. Now here's the picture of the 10G PON again. And it's saying, well, where do I place the WDM video, which combines the voice and data with the video? And then most use a single fiber to each subscriber for triple play. So LLTs for voice and data differ from video services because the signals have to be combined into a single fiber at the CO. So there's a couple choices for your multiplexing equipment. At the OLT equipment frame, and it involves placing it within the fiber distribution frame, or placing the WDM at the OLT itself. And it appears logical, but can be quite expensive in some networks. And again, the entire course gets much more in design on some of these in regards to wave division multiplexing at the transmitter. Now, there are channel spacing grids that are used in coarse wave division multiplexing. So in essence, signals can travel at wavelengths from 1270 up through the 1610 with a channel spacing of about 20 nanometers apart. Was that nanoseconds? Now I forget what that was. Nanoseconds. Yeah, nanometers. Now that basically shows you that that's coarse wave division multiplex. So I can carry signals at all those wavelengths outbound, and they don't interfere with each other, and we can communicate. Now that brings us to a basic thing of fiber to the home, is the fact that I can downstream video and at the same time uplink my other services over a single fiber. The fact that the upstream services aren't running on the same wavelength means that they will not interfere with each other. Now later on, since typically they might split to 4 homes off of one fiber as they come down your street, that means if I'm troubleshooting one house and trying to test upstream through the splitter, my OTDR can interfere with other subscribers, say downstream video signals. Okay, so how you test this is important, and what you test it with is important. And this just shows a WDM location. Now this is going to be online if you want to come back for free and visit it on our site. You're welcome to if you want to ponder over any of these, and we're always available. But these are just where you might place the equipment itself. And as I said, I'm not going to take the time to explain each and every slide. I want to get through as many general slides as I can. So here we go. If you look at the numbers, you consider the number of optical line terminators. So current and future possibilities, 3,200 homes passed would require at least 100 WDMs. So you plan ahead, either floor space back at the central office, or you put fewer homes per optical line terminal. Then you consider incoming fiber count. So outside plant cable would be sized to meet those demands. So this is a good rule of thumb for a little webinar like this. You know, how many fibers do I put up there? If I were to pass 3,200 homes, that requires at least 100 fibers back to the CO. So with up to 432, more likely depending on network strategy. So the fiber counts might be overbuilt, but you want to ensure future capacity. You often see the cable TV companies, as 432 on a pole is almost a common fiber size. Okay. Again, cable management is key. We want to do high density frames, save space as much as we can. But unlike traditional networks, fiber networks are not protected, meaning there's no diverse path for network redundancy in event of a major outage. Point A to point B is what was here through splitters. So back at the fiber distribution frame, which you would consider more than 1,440, so some good numbers here. It means that you can quickly and efficiently turn up, test, and reconfigure your networks. That's basically out of the telecordia spec that you see here. Now, crucial cable management. This should not be new if you've taken any fiber class. 1, the equipment is there about to protect for bend radius protection. Remember the old 10 times the bend radius because losses occur. We need to provide connector access and, of course, cable routing pairs and some physical protection. So here you see the bend radius is about 1.5 inches or 10 times the outside diameter, whichever is greater. But it's critical to long-term performance, as you see here. And then connector access. Toolless access front and rear without disturbing the adjacent. And testing at OC 768 transmission rates. So this is pretty basics for any fiber optic network and links. And here number 3 was you got to be neat, clear paths, easy to follow, maintain bend radiuses, high density systems. You got to easily follow the paths, be able to track things out almost by just looking at the box where you can easily, you can see this picture here of one deployed in the field. Most components are available up front and with easy access. So how you manage it. The other is physical safety concerns. Since there are high-powered lasers from central office, they can be harmful to technicians. And since they're not visible to the eye, then you must take precaution, like built-in laser eye safety fixtures. So they can be designed with the connector ports contained within a tray, or connector ports which are angled out or fold out so that at any given time they're not within the line of sight of a technician working on them. And that's what I mean by the point-to-point. And also at the CO. Here's a picture of an incoming cable at a cable TV project. I think that was in Jersey. But now, this third module is a good topic in regards to, gee, do we splice this thing or do we plug and play this thing? So we're going to take a little bit about splicing versus, doing connectors. Well, originally, these inexpensive, what we call cladding alignment splicers or fixed V-grooves were said to have been a result of, say, the nationwide FiOS projects where we wanted stripped down cheap tools or splicing machines that subcontractors could afford to buy, and we could conventionally splice the system. So think of that as one of the original goals. It was a low initial investment, these cheap fibers, but then I can always outweigh that about a plug and play or what type of connectors. So do I use fiber connectors at the hubs or FTTHs? Or do I splice everything like a conventional outside plant person would? And the answer could be both, but the reality is, even though connectorization, either pre-connectorized or field connectorization, adds a lot of losses, it's offset by that take cost and the cost of a splicing technician versus a lower level technician or installer doing the work. So the connector interface ports, as a plus, provide ease of troubleshooting, reconfigure, and ease of turning up services, especially when I may build out a 100-home development and only have 3 people a week sign up if I have that. So you can do either, and you may see at various deploys in the field either, but there are some reasons about splicing or not versus connectorization. A lot of things today we see, especially in a FiOS, tend to be plug and play with allowing the cost of the connectorization. The first thing you want to do is, why would I replace spliced hardwired with connectors? And it's about test points. The fault isolation on a network, and here they say the fault desk and the central office all the way out to a home or a building. Well, if I had to splice everything directly to the splitters, then I would have to send a high-paid technician to break the splice, connectorize it to shoot back to the central office, and then repair that splice. If everything is connectorized, then a lower-level technician, that testing, can go out and unplug and shoot back to the central office, unplug and shoot down to the hub at your street, unplug and shoot from there to your house. So when you think about easier testing access, is why you'll see a play with connectorization or pre-connectorized that you wouldn't see in traditional outside plant cable constructions. Now, I did throw a couple testing slides up here, and you heard me say earlier that it's very difficult to get a good OTDR trace. So therefore, I'd probably want to disconnect at the FTTH and shoot back to the central office. And here is just what the OTDR might typically tell you as you hit a coupler and you have a dramatic drop. You saw the splits. Some of them could be 9, 10, 17, depending on the splitters, dB losses through splitters. And the OTDR is basically only capable of really following one trace if I shoot through at a time. I might get something that looks like a coupler loss that you see up here. So the 1x30, it's difficult to decipher once the trace hits a 1x32 splitter. So here you see a 1x4 shooting downstream and a 1x4 shooting upstream. And I said that it is very difficult to decipher. You're not going to shoot all the way back. So standard practice typically would be disconnect the house from the curb, shoot that, go from the curb back to the FTTH, take a test that, and then go up to the FTTH and shoot back so that you can eliminate some of these issues. I also alluded to, and this is a problem with PONs in general, whether you're indoors, commercial with local area network, passive optical local networks, or out here, is that if 3 neighbors are connected and receiving video signals, and I go to the house and shoot to the curb, a non-PONS OTDR would interfere with the video signal being received by the 3 other houses. So when you see a PONS OTDR, it is capable of letting you know that it is active downstream, meaning you haven't unplugged. You've got incoming video coming in. And it can compensate for interference on the other 3 houses attached to it. So when you hear that you must have a PONS OTDR, it's not so I'll see the same type of trace, but it does have some protection and some warnings that I am on an active circuit, as opposed to when I disconnected the circuit, and I don't have to worry about other users on it. So one describer served by the splitter is reporting the problem. Most likely it's somewhere between the OLT and the CO, which is the fiber terminal in the field. I don't need to read that to you. And here's what I tell you. Test access points on each home. Requires you to tap the NID at each residence, which are easily acceptable. And the splitter in the fiber distribution terminal as a centralized demarc would give you access to any fiber to any of the multiple homes. Now, when things are spliced, is what I mentioned just a little bit before, that a high-level technician with splicing has to break it, test it, and then, as you see here, has to redo. So this is a very expensive way for the service provider to fire up subscribers, especially on a 1 and 2 basis. But it is about the connectorization. It's about easier test access. So I can access the distribution and run the OTDR as I just described. I might have to splice them back together, but plug and play, I could just plug them back in. So it's not always all spliced in makes the most sense, and that's where you get the connector interface, which is very, very common. As I've been describing, I can separate the links, the fiber links out. I can disconnect a splitter, test back to the curb, test back to the central office, and when I'm done, I just plug it back in. And I can also just plug in my OTDR test equipment. No fibers broken, no splicing required. So it gives 2 locations where connector turn-ups have advantages. And here's the brownfield we talk about, 100%, deploy splitters 1 at a time as needed. That's the hard sell. As I said, because chances are other service providers have most of the business in any given neighborhood. So if you're new, you have to worry about, I'm going to build this out and what's going to be my return. So in a plug-and-play scenario, I can test, fire people up pretty quickly with lower-level technicians, as opposed to if everything was spliced in or hardwired, then I have to have a real expensive splicing technician, and it's going to take a lot more time. And if I've only got 1 customer to turn up, it becomes a very expensive proposition to the service provider. So connectorize use, it's simple. You simply plug into the splitters, drop fibers are plugged into the distribution fibers, and turn-offs become simple as mating 2 connectors. Now here's just a pretty good little diagram where you see feeder fibers coming in to a factory terminated connectors. Here's 2 sets up of splitters through a cross connect. So this would be up in the hub and then out to the distribution going around the curb of the neighborhood. So these are just a couple options in the field. Now I'm going to have you, look at this later. Feel free to come back in, but you'll see that the factory terminated connectors, cord sets, everything's plugged in and cross-connected and kind of conventional to ultimately the distribution cable going out through the neighborhood. I'm not going to read all that stuff, but the pictures are interesting. Now I can pigtail splice, or you see the bulkheads here and 2 fibers going out here. Connectors are protected with dust caps. and that's an alternative architecture. So you may see a little bit of everything. Now the high-powered video signals that drive the receivers can be analog from the CO. They reach the splitter at around 20 dBm, and that's the problem with potential eye laser. So to eliminate that, the input of the optical splitter could be spliced, but it's less flexible than two connector pairs, front and back of the splitter. But it gives that easy test and reduces cost and eliminates high power laser safety issues. But it still requires a splice technician to splice those in. So you can see where the plug and play becomes more popular today than the other tool. So connectors are more expensive to splice. They add additional losses, which normally you think would be a big deal. But higher performance in manufacturing means that using today's pre-connectorized assemblies, very low back reflection, APC polished types of connectors. And in the class, we go into much more detail. That today they have a proven track record, and it's very common. So even though if you're an old outside plant guy, you kind of think too many mechanical connections, but in the ultimate, it works out better. Yes, I lose more, but two, turning people up and maintenance and troubleshooting becomes. There are things that sub-zero. Don't want to go too long, say certainly past an hour on this. But again, if you want to go back in, if you're in real cold environments, there are some things you might have to do resulting from transmission loss or microbands, how things are curved or how you put them in the splice tray. And that's about contraction of subunits, how you can adapt for extremely cold as far as expansion of the plastic buffer gel-filled tubes. You notice here you can strip all the buffer tube out of the splice closure, and then the individual fibers are free. As you said, that you can see, it says labor intensive and risky. The other apply little ring cuts to express fiber tubes, and then that basically gives a break in the tube for everything to expand and contract. I'm not going to go into a lot of detail there, but you know, now probably if you're up in Alaska, that might be an issue. Now ribbon cable typically, and notice that's what you see in a lot of the pre-connectorized now, is the ribbon cable. And it's not as big a problem as conventional loose tube gel fill, because the ribbon cables by definition are totally removed from the tubes anyway. So they're available, so they present different effects. Well, that's pretty much what I want to cover today. So bare facts, basic structure, basic networks, the impact of your video signal downstream, and we didn't go into specific wavelengths, but the 1550 tends to be your video, and the 1490 and the others are upstream and downstream. And as I said, this is just part of what's available in our FTTX installer. So this is basically the first couple of sections, so we cut it short. I didn't know if anybody had any questions or not. Now's the time to ask them, because in a little short presentation, it's often very difficult to cover everything you might. And again, I just wanted to drive home that you do have a plug and play. You do have the option, of course, to splice conventionally, which is not that common anymore. And although you have a lot of high losses through splitters and through connectors, it is much more beneficial and expensive of installing, running, and adding users one at a time to the system. Okay. Okay, apparently, how do I get presentation and video? The actual presentation will be on our website, fiberoptic.com. You can have access to, and it'll be up probably in a day or two. Give us a day or two. This is being recorded, so you can go ahead and replay it at no charge. As again, this is just a sampling from the full class. And with that, I think we pretty much got the questions. Anything else? If not, I'm going to go ahead and sign off and just wait a day or two, and you can review this at your leisure at the fiberoptic.com website. Thank you for attending. And it's fiberoptic.com/webinar as you see on your screen. Thank you very much for your participation. Have a good evening.